at 5, we want to look at the first 5 results in our results set. So how many true positives do I have here?
Three.
Yes, exactly. So we have 3 results that are returned that are actually true. And then how many do I have in total? Well, that is kind of like the number that is here, right? Exactly 5. So the precision at 5 in this case is 3/5. So I feel like this should be quite straightforward. Then we do the same for 7. So we break this up. We only look at the first 7. So how many true positives do I have in my results? 5/7. Exactly. Great. 7 is the total. And then lastly, we can do it for precision at 10. So if we look at everything, 6/10. Perfect. Yes. I hope it's not assumed that we know Shakespeare. No, exactly. I also wouldn't know. I feel like in that case, it would be either really obvious or they would tell you in brackets like, this is Shakespeare, something like that. But yeah, so these are the precision at K questions. All right, are there any more questions about this? Yeah, 6/10 is indeed also 3/5, so I guess this would be the same. So what does precision at K show us? It shows us from our results how accurate is our model, basically. If we have some kind of ranking model and it retrieves these, and with precision at 5, it has 3/5, and with precision at 10, it has a 6/10, then you could say, okay, we have like 60% accuracy kind of for our model. So that is what it tells you. Okay, so if there are no more questions about this one, well, we're right on time. So we finished ML models and evaluation, and then we have a 15-minute break now, and then at 10, we will continue with the naive Bayes classifier. Yep. And then we'll just see how fast we get through it, and then how many, it depends on how much time we have left, but I prepared quite some exam questions, and we can just go through them until we run out of time, basically. Yeah. Okay, so let's have a little break, and if you have any questions, let me know. I don't really get the precision at K is useful for collaborative filtering and ranking. Should I know this logic more in depth? I feel like for this one, you just have to know how to solve it. But why it is with collaborative filtering and ranking? Well, with collaborative filtering, it also gives you a recommendation, right? So it's based on the top result, kind of. But let's say, okay, I have this ranking algorithm, and it gives me these 10, and it gives me these 10 documents, and I want to know, okay, how accurate is my model? When it returns me 10 documents, only 6 are actually from Shakespeare. So I would say it's like 60% accurate with its ranking. So, yeah. Yeah, for example, for collaborative filtering, then it would indeed show you like a recommendation based on what you had before. And then if you then tell, like, you can also tell Netflix, like, okay, I actually don't like this, or I do. Then you kind of tell it, okay, this one is actually not accurate, but these 2 books or films I did like. So based on that, that's how precision at K works. Is collaborative filtering usually supervised? I feel like it is. Because if it's like based on, you need to know like previous information about what you like, right? If you have a recommendation system and it's just making assumptions with unsupervised learning, then it's not really giving you the right recommendation. just think about like how Netflix works, which with its recommendations, I feel like it has to be supervised, right? It needs to know, okay, which films did you watch, which ones did you like, which series do you rewatch the most, stuff like that. All right. So let's meet again at 10. Okay, wait, I'm seeing a very long question. Okay. I saw that you rounded the precision and recall, and I know you said to round if it asks, but in that particular question, it did not ask you to round, so should I just cut it off at a particular point? Will the TAs look over typed in numbered answers to ensure that if someone rounded or added a decimal value or something that it won't get marked off? I was wondering the same thing. Okay, so so I know that like in the previous exams, I believe. Let me pull it up. Yes, they don't have the 2020 exam solutions, unfortunately. Wait, let me see. So if I go to one of the exams, or was that in the solution? Ah, that's in the solution file. Because there... Hmm. Okay, I feel like honestly here it says, for example, I don't know what this question says, but oh yeah, the recall, for example, they would the answers they would mark correctly are 0.6, 0.60, and 0.600. So I feel like they have that kind of built into the test vision system. So I usually go for like 2 or 3 decimal points, right? Just kind of what feels normal, I guess. And if they really want you to give something, then they will specify it. So usually with the Bayesian networks, they say like, give me 6 decimals, stuff like that. But as you can see, like with precision and recall, they gave you these options. So I can't really tell you like it's right or wrong, because in this case, they took that into account. And then whilst grading it, you could see all 3 of those would be correct. I feel like they have that in most cases. Like with the Bayesian network, like the easy questions where you just have to read it off, you literally just take the value that has been given. I actually have the 2020 solutions because it was up. Yeah, I think they gave you the 2020 solutions from like another exam, which is weird. I can like check the Canvas page from last year. Let me see. Okay. So exam 2020. So on the sheet it says 18th of December. And then the solution says, oh, 19th of December. Wait. Is this the one with the... I'm just going to send them both to you. Tell me if this is the one you need. So this is the exam. And then this is the solution. Are those the ones you need? I send them in the group chat. I think it is the one. So, oh, that's nice that Stefan said he doesn't have it. I literally just went to the Canvas page from last year and it was there. So nice. Great. Love it. I think one of them says like 20 or November 18. The other one was said November 19 or something. Maybe I should send it in the Discord as well. I'll do that after this. No problem. Okay, Discord. Yes, okay. So afterwards I will send it in there. I think it's best if it comes from me because then they know like how I got it. Yes, okay. Great. So we just did that one. Oh yeah, that's really small. That's good. Yeah, I think the one exactly like the solutions that were from the midterm, it was like first partial exam. I remember seeing that somewhere. So maybe the one you downloaded wasn't the one from this one. That's good. Okay, I shared it in the Discord right below the announcement when I said we didn't have it, but yeah. Yeah, I'm sorry. like I had to do it in the announcements, right? For everyone to see, but it felt like my first instinct was to look at the canvas page from last year. I don't know why he didn't check it, but oh no, I hope I don't. I'm sure he tried to find it. Okay, now that we have the mystery solved of the 2020 exam, let's move on with our second topic. So that is the naive Bayes classifier. Okay, so let's see. So naive Bayes is a classification algorithm or classification method. And the input here is data which belong to certain classes, and you want one set of data with an unknown class. And basically the output that we want is to calculate the probability that the data belongs to a certain class using the following naive Bayes formula. So what we want, again, you just have some data and you have classes. So if we have certain sentences, a few of them belong to the Canvas page, the other one belongs to the Canvas page of another course, and you get a sentence with an unknown class, then based on probability, you could maybe see, okay, which one would it be classified in? Would it be classified for the one course or the other course? So that's how naive Bayes would work. So there is a little step plan. So you decide what are the main features of the data. So those are usually given. Like what are the words that we're looking for, basically. And then the second step is to count the occurrences of the words in all of the data. So which words are in the first few sentences, which words are in the unknown data. That way you have this entire table containing all the data you need. Then the third step is to define the probabilities of this data belonging to one class or the other. And you calculate those probabilities based on the data that you have. And one very important thing here is to use Laplace smoothing if needed. What does this mean? It means that if we have a 0, we smooth it, so it becomes a 0.01. So as you can see here in the formula, it's a multiplication formula. So if one word does not show up in the class, this would get a value of 0. But since it's multiplication, then immediately the entire thing would be 0. So that's why we apply smoothing, such that the 0 becomes a very small value. So it doesn't influence the probability as much, but also it makes sure that we don't get 0 immediately. And then the fourth step is to apply the naive Bayes formula to find the class with the maximum probability. And then based on that, we know, okay, our unknown data is then classified in this class with the highest probability. Okay, so let's do a recap question immediately and then go back to the step plan and see how it works entirely. So there are 5 documents about 2 courses. One is about intelligent systems and the other is about distributed systems. And we have these 5 documents containing these sentences. They give you that 1, 3, and 4 are about intelligent systems. So 1, 3, and 4 have the class intelligent systems. And D2 and D5 are about distributed systems. So that is given to us. They want you to use the Boolean features for logic, intelligent systems, distributed, and algorithms to predict whether D6 is an IS class or a DS class. So again, if we look back at our step plan, the first step was to decide what are our main features. These are usually provided, and as we can see here, our main features are these: logic, intelligent systems, and then distributed in algorithms. So that's our step 1. So that is done. So step 2, we want to count the occurrences of the words in all of the data, and you want to find which words are also in the unknown data. So if we have these sentences, and we want to put it in our little table here, so we have our 6 documents. One of them is unknown, has an unknown class. The other 5 had been given which ones are the classes, right? So we said that D1, 3 and 4 are IS, and 2 and 5 are DS. And this one is unknown. So this is like our objective. This is what we want to know in the end. Then we fill in everything we know. So we have the words logic, intelligent systems, distributed, and algorithms. So if I would write this down in a Boolean feature way, so what does that mean again? We would have like zeros or ones, right? Or trues or false. So if we look at logic, intelligent systems, distributed, and algorithms, how would I write down like what is in this sentence? If I want like a 0, 1, 0, 0 kind of like that, how would I write that? 1, 1, 1, 0, 0. Yes, because we have logic, we have intelligent, and we have systems, and the other 2 are 0. So indeed, I don't remember if I did this with true or false or ones or zeros. It doesn't really matter. Oh, here it says true or false. Okay, maybe that's a bit more easy to understand. So let's do that one. Okay, let's also look at the second one together. So we have this sentence and we have the same features. So in Boolean logic, what would that return? Zero, 1, 0, 1, 1. Exactly. So true, false, sorry, the other way around. False, true, false, true, true. Okay. Let's do the third one lastly, and then I'll fill in the rest. So we have intelligent algorithms and logic are crucial. True, true, false, false, true. Exactly. So we have logic, intelligent, and we had algorithms, right? Yes. Okay. So is this clear to everyone how we find out these true and false values? Or does anyone have any questions about this?
So when do we use the ones and zeros, and when do we use the true and false?
It's the same thing. It's just whatever you find easier, because mostly in these cases, like the question would probably be maybe like what would be the eventual probability, stuff like that. So however you want to fill in this table is kind of up to you, but I think in general they use true and false. Let me see the other one. Yeah, or they use yes or no, so it doesn't really matter, whatever you prefer. Okay, as long as it's a Boolean value, so it's true or false, yes or no, 0, 1. Okay, if that is clear, then I'll fill in the other 3 sentences. So here we have false, true, 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 and false. Here we had false, false, true, true, true. And for our unknown class sentence, we have distributed and algorithms, right? Because sentences, distributed algorithms can help reasoning in logic. So we have distributed algorithms can help reasoning in logic. So this is how we fill in our table. So that is step 2. So let's go back to our step plan. Define the probabilities of this data belonging to one class or the other class and calculate those probabilities. Okay, so what do we want to know eventually for D6? What are the 2 probabilities that we want to find? If it is IS or DS, exactly. So this is step 3. Yes, great. So we want the probability of it being an IS course, given that we have document 6. That's what we want to know. And we also want to know the probability that it is a DS course, given that we're talking about document 6. Yes, given what is true or false in D6 table. Exactly. So based on these two probabilities, in the end, you could say, okay, it belongs to IS or DS based on which probability is higher. That makes sense, right? So then we want to calculate these probabilities. So using this formula, I'm gonna put this formula on the other slide as well. I think that would be a bit clearer. Yeah, this one. Okay. Oh. We need this formula. So if I would rewrite P of IS given DS, what would that look like? Maybe someone can unmute it themselves. What do you think if we would rewrite that formula? Given
Is it then like IS given that logic is true, intelligence is false, system's false?
Yeah, almost. I feel like, so you see here, this is the class, right? So IS is the class. And then if you would write them down, then the class actually comes after the given sign. So I think you said IS given logic, but then we would do logic given IS. So what you said is indeed correct. You just need to flip them around.
Okay.
So I think you mentioned it was for D6, right? So I think that was also said, given what is true or false in D6 table. So that is indeed the case. So for intelligent, we have false. So we want to find the probability of not intelligent given IS times the probability of not systems given IS times the probability of distributed given IS and algorithms given IS. I think this was just the naive Bayes formula, right? Let's see. Yeah, so naive Bayes, they're all they're based on Bayes' rule, but from that, you can also infer that, yeah, exactly, I see it here as well. So I would say the naive Bayes formula. Does anyone know why it is called naive? That's maybe a theory question. Kind of, yeah. But there it is, I mean, it's all Bayesian, right? So it's all, in the end, it's all based on Bayes' formula, and it's like within different, like it has been proven to be different, or you can, how do you say it? You can infer this from that formula. So they're all based on the same thing. Why is it called naive? Because it assumes conditional independence. Exactly. So that is very important as well. Maybe I'll put that here. So why is it called naive? It assumes that all features are so that could be like a theory question. So that is indeed the case. So in this case, when you're multiplying all of these together, you're assuming that they're independent. What does this mean exactly? Well, if you would have, let's say two occur, so this is not really the case with words, but let's say if I say it's raining and the train is not coming and I'm frustrated, right? Yes, so that could mean that the probability of one is reliant on the other. So then in that case, it kind of gets rid of that assumption entirely, such that you can just calculate the probability like this. Because otherwise, if it was dependent on each other, then the probability of one thing happening could be actually reliant on the other one. So that could be the reason why you get this certain value. But if that is not the case, if they are all independent, then we can just treat it as independent occurrences and just get the probability value that we're having. But indeed, as Omer says, it means that the probability of one is not reliant on one of the other. If it would be, then this probability could have a certain value that is based on, because it's reliant on another one. The probability of what though? Like the probability of logic and yeah, for this one it's a bit hard because it's just words, but you could have a Bayesian classifier. I think that was in the other one we'll see later on, this one. So whether it is cold and it snows could be reliant on each other, right? Because it has to be cold in order to snow. Stuff like that. So these are actually dependent on each other, but naive Bayes is classifying them as being independent such that we can use that formula. Does that answer your question? Okay. So it is hard to see it with the words, but in this case, it gets more clear. So we'll look at that one in a bit. But just for the theory, you just need to remember, so why is it called naive? Because it assumes that the features are independent. They don't have anything to do with each other. They don't rely on one another. They don't influence each other, which is usually not the case with probability. But because we assume that here, that is why we can use this formula. Okay, good question. So let's see, we had our formula. Are we missing anything here? So we have all the features dependent on the class, but I'm also seeing this here. So what does that mean? Do we need to add anything to our formula still? Exactly. We also need to multiply it by the probability that it is an IS course. So do not forget that. So it's right here in the formula. It refers to this C, which is the class. So you do it times the probability that something is from the IS class. Okay, so we do the same for distributed systems. So that is logic given distributed systems, not intelligent given distributed systems, not systems, distributed, I'll keep writing these things, and algorithms. And then, of course, we also have to multiply it by the probability that it is a DS course. So that is very important. Okay, so that was our step 3, kind of halfway done. So we want to define the probabilities of this data belonging to one class or the other. So that's what we did here. Now I want to actually calculate these. So for this, I made a little separate table. So we wanted to find logic, not intelligent, not systems, and then distributed and algorithms, right? That is what we want to find. So if we want to know the probability that logic given the IS course, how could we see that from this table here?
Count how many times the logic shows up in the IS courses.
Yes, exactly. So let me pull it up. So in our case, what would be that value? What would be that probability?
2 out of 3.
Yes, exactly. 2 out of 3. Because we're looking at only the occurrences where we have the IS course. So this line, and that line. How many times does it involve logic is true? 2 out of 3 times. So then indeed, this would become 2 over 3. So let's do the same for the DS course. So what is the probability that we have logic given that it is a DS course? Yeah, so someone's saying for the other one, they said 2 out of 5, but make sure that we're talking about given IS. So that's why it's 2 out of 3. Let's say for the other one, I see someone saying 0 and the other one saying 0.01. That is indeed true. Remember, use Laplace smoothing if needed. So 0 always becomes 0.01. So that is very good. Indeed, this one is 0.01. Okay, let's do the same for not intelligent. So what is the probability that it is not intelligent given IS? (0.01 exactly. And for DS, so not intelligent, 1/2 exactly. Because if we look at the DS, this one and that one, probability that it is not intelligent is 1/2 times. So that is indeed the case. This is 1/2. Okay. So we do the same for not systems. So let's just do one more together. So for not systems, given that it is an IS course, how many times is that the case? 1/3, perfect. I see someone saying 2/3. We're looking for not systems. So that is something important to look at. So we want to know this one, this one, this one. How many times is it false? Yes, exactly. No, it's good that you saw that. So then that is indeed 1/3. And then for, let's do the final one together, not systems given distributed systems, 1/2, perfect. So is that clear for everyone, how we find these values? Yes, okay, great. Then I'll just fill in the rest. So this is 1/3, this is 1/3, and this is 1, because if we look at distributed, for distributed systems, it's true in each case. So then we just get 2/2, which is 1. All right, perfect. So we have our formula and we have our probabilities. So the last thing is to apply the formula to find the class with the maximum probability. So we take our formula from before, and we take logic given IS, so that is 2/3, times intelligent given IS, times not systems, distributed, and algorithms. And then we should not forget we need to multiply it by the probability that something is an IS course. So how do we know that? What is the probability that something is an IS course? 3/5, exactly. And why is that? Because we have 5 documents that are in our given data, and from that we know that 3 of them are an IS course. So the overall probability of it being an IS course is indeed 3/5. So the value that gets out of this is 0.00148. Okay, let's do the same for the DS course. So we're basically just filling in the values from our table here, because those are the probabilities that we just defined in the formula. So we take 0.01 times half times half times 1 times 1, and do not forget, times the probability of DS. So what is that in our case here? It is kind of the complement of what you just had. So indeed 2/5. So the probability that something is a DS course is 2/5 in total. As you can see, this is 3/5, this is 2/5. Together they make 1. So here we see the answer for this one is 0.01. Okay, so then our final step was find the class with the maximal probability, and then we define that as the class from the unknown data. So looking at this outcome, what is the conclusion that we could draw from this? Okay, I see DS, exactly. So we know that DS given D6 has a higher probability than IS given D6. So D6 is from the DS course. Exactly. If there are only 2 outcomes possible, shouldn't it be equal to 1? Well, this is a conditional probability. So if it would be equal to 1, then you would have something like IS or not IS. Then it would be equal to 1. Because it's like the kind of the complement of the thing happening, but PS given D6 is not, it shouldn't be 1, no.
But I meant like if they can only talk about two subjects, like IS, it can either be that they're talking about IS or DS. Like surely then it would be like I get the formula and everything, but I don't get how it can be so low if it can only be two outcomes.
So do you mean like these two outcomes should sum up to 1?
I don't know if they should, but I get the formula. I'm just wondering why it's so when it's like
okay. So I feel like if you have a conditional probability and you want something to sum up to 1, then you need the thing happening and the thing not happening, right? So like I said, if you would have PIS and P not IS, then this is like all that could happen, right? This is the entire event. So then this would sum up to 1. That is why this one is 3/5, this one is 2/5. But in this case, with the conditional probability, you're multiplying everything. So in the end, it's not about like to get a probability vector of both of these, where the sum is 1. You just want to know which one has a higher probability of happening. So that is why it's not equal to 1. You just want to know for these two events, given some information, what is the higher probability of something happening. So you shouldn't really see it as one event. You should see it as two conditional probabilities, like separated from each other.
Okay, thank you.
Yes. Okay. I think there was something in the chat. Why did we get DS? Yeah. Okay. So with the 0, oh, I think you meant in the outcome. Yeah. So this value is higher than that value. Yes, exactly. Great. Okay. So then DS should indeed be the course. So let's do another recap question. In this case, there's a clear correlation between the weather, the NS operates smoothly, and my level of frustration. So from this, like we said before, like the cold and the snow and the wind could be dependent on each other, but we assume that they're independent in this case. We want to apply naive-based learning with the smoothing of 0.01 on this data to predict whether I will be frustrated on a day. So there's like a new day where it is not cold, no train, there is wind and there is snow. And we don't know, am I frustrated or not? So again, this is our objective. What is the classification for that day? Okay, if we go back to our step plan, it says decide what the main features are and count the occurrences of these words or these things in the total data. So these two steps have already been given to us. No train is cancelled, so then train would be yeah. This is a bit of a weird question. They're actually using so train cancelled. No train cancelled means that we get no here. So that is a bit of a weird question. It's a bit ambiguous. So I feel like they wouldn't really. I think they specified in the solutions like this was worded a bit unclear. But in this case, they're using train. No train means no in this one. Okay. So like I said, for the first two steps, we had to define this table, right? But this has already been given to us, so we don't have to do the first step. The second step, well, we just did here pretty swiftly. So we just said, okay, no, no, yes, yes. So then we go on to the third step already, which says define the probabilities of this data belonging to one class or the other. So remember here we said IS given D6. So in our case here, how would I write those two probabilities down? So again, it's given D6, but what do I want to find out? Whether you're frustrated. Yes, so I saw yeah, so yes, saying D6 is a bit, is not that clear. So indeed, we want to know, am I frustrated or am I not frustrated? So that is indeed how you would do it. And how would we write down the entire formula? Well, we do the same as here. We apply the features that have been given in the table for D6. So in our case here, we take the probability of not being cold given D6 times no train given D6. And what does it say? Windy and it snows. So windy and snow. Correct? So we do the same for not frustrated, of course. Oh, wait, I'm missing something here. What am I missing? Oh, wait, I'm doing this wrong. I'm sorry. Yes, exactly. It's given frustrated. I was like, wait. Yes, okay. And then also times PF, that is correct. So indeed, I want to know for frustrated, and I do the same for not frustrated. So you could either make the table again, or because we've been given the table here above, we could just read the values of the table. Okay, so if I want to know the probability of being frustrated given D6, what is the probability of not being cold given frustrated? I see 1/2. Okay, exactly. And why is this? Because there are two cases where I'm frustrated, and the amount of times that I have the no for cold is 1/2. So that is indeed the case. So what is the probability of no train given F? 1. Does everybody think 1? Yes, it should actually be 0.01. Because we're looking for no train. So we're looking for the amount of times that train says no, which is 0 times here. So instead of 0, we apply smoothing of 0.01. So that is indeed the case. And then for the rest, so wind and snow. So looking for the amount of yes in wind and snow. Yes, they're both 1/2. Perfect. And then lastly, I want to know, what is the probability of being frustrated? 2/5. Perfect. Because we have 2 instances out of our 5 pieces of data where it says that I'm frustrated. So there we get 0.0005. And we do the same for not frustrated. So does anyone want to give me any values? What is the first value? So now we're looking at these 3 sentences. One over 3. Okay. For the second value, I want to know no train. Yes, perfect. 2/3. And we do the same with the rest. So for snow, we have no instances, so we get 0.01. And for wind, we get 2/3. Sorry, then this should be first, I think. Wind is 2/3.
Mara,
Yeah.
I'm still confused about for the PF given D6 why yes for the trains one why it's like no or whatever.
Yeah, it's just weirdly worded in this question. So basically it says just no train corresponds to a no in this table, but it is the question is a bit too ambiguous. So in the exam or any other question, it will be clear like what you have to assign it. But yeah, I cannot really give you any other answer than it's just. Yeah, so no train is cancelled. So it would actually be train cancelled. Yes, exactly. That's what they're kind of getting at, but it wasn't that clear. So yes, indeed. And then the probability of not being frustrated, well, that is 3/5, right? Because there are 3 rules here instead of 2/5, which you guys said. So we get our probability 0.00089. Okay, so again, what is our final conclusion here? Our very last step. Will I be frustrated or will I not be frustrated? Exactly. So, not frustrated, given this day, is bigger than being frustrated. So indeed, I will not be frustrated. Okay. So are there any more questions about naive Bayes? If you would apply this step plan, applying smoothing, using the formula, anything about this? What if we have the same probabilities for frustrated and not frustrated? Then it will not really be classified, I think. Then it will just be indecisive in the end. You could say then PF is equal to P not F. So, like not decided or something. Decided. Like that. But usually if you would have like a multiple choice question for this one, they give you like some options. So you could say like PF is bigger than P not F, or they're equal, or I apply smoothing in some way, or stuff like that. So I guess it could happen, but in this case, when they just ask you like, okay, what is the class, then you get one answer.
But if I understand correctly, the probability of frustrated given the 6 is 0.005.
Mhm.
And the probability that's not frustrating given d6 is 0.00089.
Mm-hmm.
But frustrating is bigger, right?
Well, if you compare the values, which one is bigger, 5 or 8?
Wait.
So
Yeah, okay, I see it.
yeah,
Yeah,
okay,
okay.
great. Maybe the zeros were a bit confusing, but indeed, so not frustrated will have the higher value here.
Yeah, because of the indent. Sorry.
Yeah. Oh, okay. That makes sense. Yeah, maybe I should like write them down so they're a bit more like that. I think that's better. Okay. All right, great. So let's see. We finished this one. Maybe if we continue for 5 more minutes, let's see, what is the theory here? Okay, I can maybe go through theory points for 5 more minutes, and then we can have a break, because I think the longer we go on now, the more time we have for the exam questions in the end. Or we can take a break now, then start, and then like move the breaks a little bit further. Continue? Okay. I'll just continue for 5 more minutes then. I think it's mostly theory. But okay, so we just did the naive Bayes classifier. Yeah, exactly. I think the exam questions are the most important part, so that is good. So now we're going to talk about text features and k-nearest neighbors. So we have something called k-nearest neighbors classification. So what is this? This is used to classify unlabeled data. Again, we have some unlabeled data, and we want to find the most similar case and copy that label. So in the naive Bayes classification, we're kind of doing something similar. We have unlabeled data, and based on probability, we classify that into a certain class. But here we look at what is the most similar, and we copy the label. So let's say we have all of these assignments, and they correspond to the AI course. This one is chemistry, and this one is law. And we've been given some unlabeled data. And then with k-nearest neighbors, it looks at, okay, what are my nearest data points? Like that. And based on that, these 4, let's say, k-nearest neighbors here is 2. You could define that anything you like. You could say k-nearest neighbor is 3. Well, then I could say, for example, okay, these are my 2 nearest neighbors. These are my 3 nearest neighbors, and they are all classified as AI. So I will copy that label, and then my unlabeled data will become AI as well. So this would be with k is 3. It would choose these 3 as its nearest neighbors, and it would copy that label, namely AI. Okay, so that is kind of what's happening for k-nearest neighbors. So then we have, we want to see if 2 texts are similar, if their constructed feature vectors are similar. So we use that using text features. So how can we measure this? We have 3 ways of measuring whether texts are similar, namely Euclidean distance, Hamming distance, and cosine similarity. So let's just go through all 3 of them together. So here we have the Euclidean distance. So as the name suggests, it talks about distance, right? So smaller value means a shorter distance, so a closer neighbor. So in our case, if we look at the neighbor, we want to find the smallest values. Correct? So that is why it says distance. We want to find shorter distance, smaller value. So let's look at what this formula here means. It might look intimidating, but it's not that bad. We see a value for P and a value for Q. So with feature vectors, text feature vectors, we have, again, Boolean values, so like 0, 0, 1, 0, stuff like that. Something like this for certain words. So this is word 1, this is word 2, word 3, etc. And here you're kind of comparing each word from each different sentence. So this is sentence A and this is sentence B. So Q1 and P1 is this first value and that first value. So let's see what happens if we would fill this into this formula. So let's say Q is 1 and P is 1, and we square this value. What value do we get there? Zero, exactly. So if they have the same value, they're 0. Let's see if they are, when they're both 0, then it's also 0, right? So this is when they have the same value. Oh, that's okay. So same value. Now we want to look at, okay, what if we have 1 minus 0 or 0 minus 1? What value do we get there? Now it's 1, exactly. So this is when they have a different value. So when they have 1 and 0, we would turn a value of 1 or 0, 1. And when they're the same, so if they're both 1 or both 0, we get a value of 0. So what does this mean? Euclidean distance, in a sense, is just sum up the amount of times where Qi is not equal to Pi. So this is where Qi is not equal to Pi, and this is where Q is equal to P. This is kind of difficult. Will we also do some practice questions on this? Yes, certainly. Yes, okay, that's good. You can save your questions for later. This formula is given on the cheat sheet though. Is Euclidean distance always calculated with zeros and ones, or can it be any number? With text features, we have zeros and ones because we're just looking for, is this word in the sentence, yes or no? So you don't have to worry about 5s and 7s and stuff like that. You just have two sentences, A and B, and they have some feature vectors, and you compare these. So if we compare 0 and 1, so let's just check, okay, what is the Euclidean distance of A and B here? Okay, we check 0 and 1. That is a difference, right? So that is 1. These two are also different, so we get a 1. Here they're both 0, they're both 1, they're both 1, they're both 0. Okay, so my Euclidean distance in this case would be 2, and we take the square root of it, which is just the final step. And take the square root of that value. So for A and B, this is just a little example. Maybe this makes it more clear. You just count the amount of times where they are different. So let me just take another color. So here they are different because we have 0 and 1. And here we have 1 and 0. For the rest, they are the same, right? This is 0 and 0. This is 1 and 1, 1 and 1, 0, 0. So if we would add these up together, or subtract them from each other and square it, we get 0 values. So we could add them, I guess. We could do 1 plus 1 plus 0 plus 0 plus 0 plus 0. But in the end, what this comes down to is we're just summing the amount of times where they are different, which is 2. And then you rewrite that such that you get the square root of 2. So does this make it a bit more clear already, Rufan? Yes, okay, great.
I have a question how the formula is like shown. Why is it that it's like sum equals I equals 1 to n, but in the previous formulas it was just sum I? Like really long time ago, yeah.
Oh yeah, maybe a longer time ago. But in this case, it says I is 1. It basically just means for every single one of these values. So you have Q1, Q2, Q3, Q4. That just refers back to every single text feature, basically.
And then n is how many it goes back, right?
Yeah, exactly. You just take every single one of them. That's what it says.
But it's the same as having sum I, or no?
As what? Sorry?
Having the sum sign and just an I.
Yeah, I think maybe it was like the error value.
Yeah, it was like really far back.
This one. Oh, yes.
Yeah, there, like sum I.
Okay. Well, but there you also take every xi and every yi. So I think it's the same. Yeah. N just means how many times you need to add. Yeah, exactly. So if we go back to this one, the N here stands for the total amount of bits. I think this just means the how big the step is, right? So you take every single one of them. But in this case, just remember, yeah, start counting at 1. Exactly. Okay. So in this case, you just remember sum the amount of times, yeah, up until n. You take I is 1 for each single word. So you take every single value and you sum the amounts of times where pi is not equal to qi. Okay. We are at 10:45, so maybe let's have a break here. We could also do a shorter break. I'm really not sure how, because we have one thing after this as well. Oh, maybe it's okay. Because if we take a break right now until 11, we do this one. And then I think design matrix, linear regression, neural networks. Okay, we can also take maybe a 10-minute break until 11. Maybe that's better. I'm just trying to like figure out how much time we'll have left for the exam questions. So let's take a break. I will keep this slide up. So then we have a break until 11. So we let this sink in, the Euclidean distance, and then we'll look at the other two afterwards and we'll do some example questions. I did see though that okay. Stefan sent in the Discord that it's not exactly the same as the exam 2020 as I changed the questions later. So you might find some answers in there, but not for others. That might be confusing, but it indeed can be useful. Just be careful. So just to point that out, the cosine formula is not on the cheat sheet. Is that on purpose? I feel like it would mean that you don't have to use it then. I think. Because the cheat sheet is like it provides you with stuff you need. So we will just go through it anyway. But maybe that implies that you're probably using one of the other two. But I would definitely just understand it. I think that's important. Okay. So let's have a little 10-minute break now. Okay, so it is 11. Let's start again. So we just talked about the Euclidean distance formula. So now let's talk about the Hamming distance. So the Hamming distance, again, it talks about distance. So smaller value means a shorter distance and thus a closer neighbor. So the Hamming distance formula is quite straightforward. It just takes the amount of bits that are different divided by the total amount of bits. So here you see a little man looking at some feature vectors. It says, okay, it differs in 2 positions. So the Hamming distance is 2, and then we divide it by the total amount. So here that's 1, 2, 3, 4. 2 out of 7, let's say. So that would be the Hamming distance in this case. So I feel like there's not really a lot to say about this one. So for here, you took the bits different and you then took the square root of it. This is just the bits different divided by the total number of bits. So this one's also in the cheat sheet. Okay. So if that is clear, I think there's not much to say about it. You just take the amount of bits different divided by the total number of bits. So lastly, we have the cosine similarity. So as was pointed out, this is not on the cheat sheet. So I feel like, based on that, you wouldn't need to use it, but maybe you do need to know what it stands for. So in this case, cosine similarity, as the name suggests also here, it calculates similarity. So we actually want a bigger value. So the 2 text features are more similar. So then that is the closer neighbor. So here we look at the smallest values. Here we look at the smallest values. And lastly, here we look at the biggest values. So maybe there won't be like an application question on cosine similarity, but if they ask like, how do I find out what the closest neighbors are using cosine similarity, then you would say you would have to maximize the values, find the biggest values, stuff like that. So I think that's most important to know for cosine similarity, but let's just quickly go over the formula as well. So here we see we multiply the first value by the second one. Well, let's see what happens if we try all possible combinations. So if we multiply 1 by 1, we get 1. 0 by 0, we get 0. 0 by 1, we get 0. 1 and 0, we also get 0. So what does this mean? For A and B, you sum the amount of times where they're both... Oh, sorry, yes. Thanks. Yes, that's what I meant. So for this one, the amount of times where A and B are both equal to 1, because that's the only instance where it will return a value of 1. And then underneath this division line, it says we also take the sum of the amount of times where the value of A is equal to 1, or let's say if you take the square root of 0, you get 0, but if you get the square root of 1, is that 1? Gosh, I forgot. But in this case, for this one, you just take the amount of times where only the value of A is 1. And this is the amount of times where only value of B is 1. So you can find one of these. Yeah, that's 1. Okay, great. So you can find one with cosine similarity in one of the workgroup exercises. I would just say understand the theory behind it. So we want similarity. So bigger value is a closer neighbor, but I feel like if they've not given it on the cheat sheet, that means you probably won't have to apply it in a exercise, because they say they will provide you with all the formulas you need, right? So I think that's what they're implying with that. But I hope this is still kind of clear. So if you multiply A times B, only when we multiply 1 by 1, do we get value of 1? So just you sum the amount of times where they're both 1. The double lines surrounding A and B. The double lines. Oh, these. That is I feel like that is the length, I believe. So this is the dot product between A and B. And here you're multiplying the length of A times the length of B, which you take by the square root of A, basically. But in our case, all you just need to look at is the amount of times where A is 1. Okay. So that is for cosine similarity. Again, I don't really think you would need it on the exam then, but just know, calculate similarity, bigger value, that is the closer neighbor. So we've been talking about these text features for a while. So before we can construct the text feature vectors and use the formulas, we have to take some pre-processing steps. So these usually include to lowercase the text, to remove punctuation, to apply stemming, and to remove stop words. So stop words are usually given, and if they're not, you can just get rid of the words that occur very often. So words like the, a, is, stuff like that. But then you have to be sure that you're removing every single instance of the word is. So also be and are and was. You have to be consistent with it. So that is very important. But usually the stop words are given. And again, if not, be consistent with it. Here's a little example of what stemming is exactly. Do they tell us the pre-processing steps for each question, or do we just assume that these are the steps? If they tell you to give you the feature vectors of certain sentences, then they usually give you the steps you have to go through. Yeah. But stemming in this case is you take the kind of the root form of the word. So you have the word playing, plays, played. The common root form is play, and for a word like a verb, so am, are, is, you just take the word be. Same with capital letters or apostrophes or stuff like that. You just take the word car, such that if you have car in one sentence but cars in the other one, and when you take this feature vector of car, that means that in every single sentence that word will be seen as the same word, basically. So if we have playing, plays, or played, then we just take one feature vector, basically the word play, and then they will get values of 1 for each of these sentences. But I think that will become more clear when we do a practice question. Okay, so here for text features, as you can see, you get these 5 text documents. Is entity recognition relevant? I do not think so, no. I think these and these are the ones that we've seen in the work groups, so I feel like those are the most important ones. Count occurrences. Have you seen these in the lecture somewhere, or? Okay. I feel like in that case you would have to know what it is, but then you usually get these as your entity recognition counter. I feel like entity recognition doesn't really have to do with pre-processing text features, right? Because you just want to get the words in the end. You don't want to have like the meaning behind the sentence. But I think there was one exam question about this, so we'll return to that as well. Okay, so the first one, which is about text features, it asks you convert each of these sentences into feature vectors using the following pre-processing steps, and create a table to write the vectors down like this. So if we want to apply lowercase text, remove punctuation, stemming, and stop words, and we have the sentence, a cat sleeps near the field, how would we turn this into feature vectors? So which words do we get in the end? We lowercase the text, we remove punctuation, we do stemming, and we remove stop words, which are all of these. A, B, of, in, all, because, over. what is the label behind our sentence? Oh yeah, so we have a label passive, a label active, and then remember here, what do we want to do in the end? We want to assign unknown data to the label from its nearest neighbor. So here, I think it's in the next question, we get a new unlabeled data. And based on the info that we have here, we can classify it in one of the classes. So either active or passive, or we can give it that label. Okay, cats sleep near field is indeed correct. Yeah, just keep them coming. So, field. Cat sleep near field. Cow walk full puppy. Are those just the words you're seeing, or are those the actual sentences? Because for the second one, we have the cow walks in the field. So what would that sentence become? Cow walk field. Exactly. So that's how you would write it down. Oh yeah. So I guess that's one way of doing it. But if they ask you specifically for the feature vectors, then you would have to write that down. So for the third one, we have field is full of puppies. So I think I already saw field. Do we remove is or do we keep it? Yes, we keep is because it's not a stop word in this case. So field is full, and then indeed you take the word puppy, because that's kind of stemming it already. So if there's any other form of puppy in any other sentence, we take that form. For 4, we have the cats and dogs run in the field. Yes, we get cats and dog run field. And for the last one, which is kind of a long one, we get cow is mad, cats and dog walk puppy. Like that. So those are the sentences that we have, and I think, as was said before, indeed we want to get all of the words that we have. I want to put them into this table, because as you see here, create a table to write these vectors down. Like this example, you just insert zeros and ones whenever they are or they are not in the sentence. So for this first one, we have cats sleep near field. So then where do I put my ones? Maybe it's pretty obvious, but if we have cats sleep near field, yeah, exactly. So cats sleep near field, and then the rest would be 0. So just to make sure that you understand how to fill in the table. So the second sentence is cow walk field. So we take cow walk and field, and again the rest is 0. So if you would do this yourself, you just need to check, okay, which words do I have in my sentence? Field is full puppy. So we have field is full puppy, and the rest is 0. Then we have cat and dog run field. So we have cat and dog run field. And lastly, we have cow is mad, cat and dog walk puppies. So cow. We have all of these. We don't have full puppy and mad, like that. Okay. So I feel like this was clear, right? So you apply the pre-processing steps to these sentences and you fill in the table accordingly. So now the second question is you're creating a k nearest neighbor classifier with k is equal to 2 and with the Euclidean distance as a metric. To which class does the following sentence belong, active or like the label, I guess, what would it be, active or passive? So we have the dog walks in the field. So remember our first step here was to apply the pre-processing steps. So let's do the same for this sentence A. So what are if we apply the same pre-processing steps, what sentence would we get for this one? The dog walks in the field. Dog walk field, exactly. And then indeed, we would fill in the table as dog walk field. Exactly. Okay, so then we want to use the k nearest neighbor classifier with k is 2. So what does that mean? K is equal to 2. Does anyone remember? The 2 nearest neighbors, exactly. So we want to find the 2 nearest neighbors. Perfect. Exactly. 2 nearest neighbors. And using Euclidean distance. So does anyone remember what the Euclidean distance? We sum the amount of times where qi was not equal to pi. Remember, because only then do we get a value of 1. Okay, so what we want to do is we compare sentence A to sentence 1, 2, 3, 4, and 5. Which formula is that? This is the Euclidean distance. Yeah, so if we go back, it's this one. Remember how we did that one? And then you take the square root of it. Yes, okay. So let's do that for this one. So we want to compare sentence A to sentence 1 and see the amount of differences. So I think it would be easier if I take this one and put it above the table that we just had. Oh. Like that, so we can compare them more easily. Okay, so if I compare sentence A, which is our given sentence here, sentence A, to our sentence 1. So this is 2, 3, 4, and 5. So how many times do you guys count where qi is not equal to pi? So if we go back, how many times is that the case here? We're comparing sentence A to sentence 1. Okay, so I'm seeing 5. Let's see. So cat is different. Sleep is different. Near is different. Field is the same. Walk is different. And dog is different. Exactly. So 5 times in total. So here I'll just write down the amount of differences. So 5. Okay, let's do the same for sentence A and 2. So how many differences do we see there? 2. Exactly. Let's see which ones are different. We have cow is different. And we have dog that is different. The rest have the same value. So indeed, the difference here is 2. Okay, great. Let's move on to 3. People are saying 5. Okay, let's check it. We have walk, dog, is full and puppy. They are all different. So indeed, that is 5. We do the same for sentence 4 and the same for sentence 5, of course. So for sentence 4, how many do we have? Okay, so 4 and 3. Let's see. 1, 2, 3. Which one am I missing? 4. Walk. Yes, exactly. So indeed 4. And lastly, we check A and 5. So if we compare those two, seven. Okay, 1, 2, 3, 4, 5, 6, 7. Indeed. Okay, so we go back 7. Then to do it properly, we take the square root of everything, but that doesn't really affect the answer because the smallest value is still the smallest value. But okay, this is our final table. So then, okay, let's go back to the question. We had k is equal to 2. So as you all said correctly, oh, sorry, you're right. This should be 7. Thank you. Yes. Yeah, okay, sorry. So then we want to look at case 2, so the 2 nearest neighbors. So for Euclidean distance, did we want to look at the biggest value or the smallest value to find its nearest neighbor? Smallest, exactly. So what are the smallest 2 neighbors compared to A? Sentence 2 and sentence 4, exactly. Oh, well. Sentence 2 and sentence 4. So 2 and 4 are the nearest neighbors. So what does this mean? What do we do now? If you want to know where does A belong, check if it is active or passive. Exactly. So we go back, we check the label. So we said 2 and 4 are the ones that are most similar, and they both have a label of active. So these are most similar to 2 and 4, and they have labels active and active. So A will be active, right? That's based on its nearest neighbors, which both have a label that is active. We will classify A as active based on the 2 sentences that it is most similar to, which are 2 and 4, its nearest neighbors. So that is why A will be classified as active. All right. Are there any questions about K nearest neighbor text classification so far? What if we had K is 3 and we had 2 passives and 1 active? Well, there are multiple ways of solving this. You could either check, okay, in case I have 3 of them, let's say I had 2, 4, and another one which had the same value. But since the square root of 2 is the smallest one, and this has a label of active, for example, then I could say, okay, then I choose active. Or if you say, okay, I have 2 passives and 1 active, then because I have more passives than active, then I choose passive. So in our case, if you had passive, passive, active, then it would be most logical to choose passive. What would be the label if we had active and passive for K is equal to 2? Then I would, yeah, you would just have to justify it. Then I would see, okay, which one of the 2 is the more nearest neighbor, I guess. So the actual smallest value here is 2. Let's say that was the active one. So then I would say active, or I would say like indecisive, stuff like that. But this is not an open question, so I feel like you don't really have to like justify and explain with this one. Okay. So let's see what time it is. Okay, great. We are finished with this one. So again, are there any questions about k nearest neighbors? What if we had case 3, but the third smallest options are 2 options? So which one do we choose? Okay, let's say we have k nearest neighbor is 3. Then we would have to choose 2, we'd have to choose 4, and 1 and 3, right? Indeed, we would choose both. So we know that our nearest neighbor is 2 and 4, and then either 1 or 3. So then you would have to choose, okay, am I making the combination of 2, 4, 1, or 2, 4, 3, or 2, 4, 1, and 3? Like that is just, again, you just have to justify your answer in that case. But I think for the second part of this question, well, you don't really pick what you like best. You basically, in this case, 2 and 4 are nearer, I guess, right? Because they are smaller values than square root of 5. And in our case here, you would get active, active, passive. So then you say, okay, I choose active. I could send you in the group chat like a way I did it for one in the work group where we had a equal one and you could split it in like 6 different ways. So I can send that to you. I think that's maybe better. Is that okay? Then I'll send it during the next break. Because there were multiple ways of doing it. So I think that would make it more clear. Basically, you just have to break the tie. So either choose the one that is nearest, choose the one that you see the most amount of times, say that it is indecisive. You can also say that. So there's not really one right or wrong, but you don't, I guess you, in the end, you would pick what you like best. It's just you pick what you think make the most sense in the end. But you would have to justify why that is. But again, this is not an open question, so I feel like that will not happen on the exam, but I can send a screenshot of sentence B where this was the case, and then you can see it. Or you could use a different method to break the tie. Yeah, maybe if that gives you another, or yeah, I don't know if you can just think about that. Again, I don't think they will make it this complicated on the exam. But definitely, like in the work group, we did all 3 of them and we compared them and we used different values of k, etc. So here I just sent something in the group chat where in B, I had 3 nearest neighbors, even when k was 2, because the value of 1 and 3 was the same. And there you can see like 3 different ways that I broke the tie, basically. Okay. So that was the text features and k nearest neighbors. We still have, I see, 15 minutes. So let's move on to the design matrix, linear regression, and neural networks. That's the last theory we need. And then you know everything for the exam. So that's great. So now we're talking about design matrix, linear regression, and neural networks. So let's first talk about the design matrix. So with classification data, you always try to group the same kind of data together, and you can do this by using a linear model. So here you can see we have some data which is represented with pluses and with circles, and we want some kind of line in between that separates these 2 clusters of data. Because then if we do that, we know that if we get some new unseen data and it is right here, then we know it belongs to the plus class. Similarly, if we get some new data that is here, then we know it belongs to the circle. So that's what we want to do there. So in this design matrix, what do you do if you're not able to classify them with a linear model? Well, then you have to modify the features such that a linear model will fit. So let's say we have something that looks like this. So the only kind of model that can split it is this circle. Well, that's not a linear separator, right? So what we do instead is we could kind of modify the features. So we can take, for example, that every x value gets squared, every y value gets squared, and from there we can see, okay, now we can actually fit a linear model in there. So that's just all you have to do for these kinds of questions. So there's a step plan. You draw the coordinate system of the original feature set. You provide a design matrix with the new features and then draw it again. And then you define a linear separator that fits. Okay, I didn't add a, how do you call it? A coordinate system. Is the exam on paper? No, it is on the computer.
So how would we draw it, like a new one? Or would this
Well, in the question, okay, so the question could go either of two ways. So one question could be, okay, which features would be the best ones such that I can fit a linear separator? And then you would just get, okay, A, B, C, D, which one is the best? Or you'd get a set of data points and they say, okay, what is the best linear model to fit it? And then again, you get A, B, C, D. So this is the manual way of doing it. And then there, I believe you get scrap paper. You can just draw it. And then from there, you can define your answer. But I didn't put in a coordinate system, so I'm just going to put it in real quick. All right. Okay, so let's do a recap question. So it says, consider the following training set of positive examples. And yeah, so the question could be either which modification would be the best or which linear separator would be the best. But again, it's multiple choice. So you don't really come up with them yourself. You just check the ones that were given. And based on that, you define your answer. Okay. So we have some positive examples and we have negative examples. They say draw the feature space and try to fit a linear separator. So let's do that first. So draw the coordinate system of the original feature set. So we have some positive examples. So we have 1, 1. We have 1, minus 1. Minus 2, 2. And minus 2, minus 2, like that. And then we also have some negative examples, is what they call them. So we have 3, 3, 3, minus 3, minus 4, 4, and minus 4, minus 4, like that. So that kind of looks like the example we just had, right? Can we fit any linear separator in here? No, exactly. We would have to define a separator that kind of looks like that, right? A nice circle, if I could draw one. So that doesn't work. So what do we do instead? Provide a design matrix with new features and draw it. So if we look at these examples, we have our positive data points. Does anyone have a suggestion of what we could do to adapt these values such that we could actually fit a separator between them? So I see someone saying we basically take the square of it. So instead, all the x's become x squared, and the new value of y becomes y squared. So what does this mean? That means that our positive set turns into 2, 2, 4, 4, right? Because we take the square of 1. Oh, sorry, 1. It is 1, 1, 4, 4. And we do the same for the negatives. So we look at that data set, and what do we get there? We get 9, 9, 16, 16. So let's draw it again in our coordinate system, but let's take some other steps here. So let's say like 16 is here. It's just about the idea. Okay, so let's draw the positive set. So we have 1, 1, and we have 4, 4, right? Those are our positive examples. And negative, we have 9, 9, and 16, 16. So could anyone give me an example of a linear separator? So that is our third step. Define a linear separator that fits. So here you can see it could either be like that. It could be like that. It can also be straight. It could be a straight line. So I feel like that is the easiest in our case. So what function could I define here for a linear separator? Fx is 6, exactly. That means we just get our linear separator like that, which is indeed 6 or 7. Yes, basically just anything between here. So anything between 9 and 4 could be 6.5, could be 7, could be 6. As long as it is a linear separator that separates the two classes. No, that was just kind of to like modify the values, but in our case, you just define fx. But then again, like an exam question could be, okay, what would be a good linear separator? You could have 4, 2, 10, for example, and then this is A, B, C, D. And then they ask you what is a good linear separator. Then of course 4 is maybe too low, or maybe that's not a good example. Let's say like 3. And in this case, you would choose B, for example. Is there another separator we can use? You can define a line with a slope if you want, but I feel like this is an easier approach. Of course, if they give you something like that in the exam, then you would have to draw it, but it's usually not that hard. So then it would just be like the slope is 1, or I guess you could define something like that. That would also be a linear separator. But I feel like the easiest approach in this case is just to go with this one. How would you go about defining a line? Well, you don't have to define it yourself. That's the thing. It's multiple choice. So if they give you one, I don't know what a good one would be, but they would give it to you, and then you can check it out. Because I do think you know this, right? That's how you define a line with a slope. Like y is ax plus b, and then a is the slope, and then b is the point in the y-axis, and then you could kind of draw the line. But I think I also have an exam question on this, so there you will see how you would do it. I'm not quite sure what the design matrix is in this case, as we have not given a matrix. Just the name design matrix? I'm not sure why it's called design matrix. Yeah, I assume it would be a matrix. I don't know why it's called a design matrix, but if I Google design matrix linear regression, then I guess you could do it in a matrix way. But in our case, we're just using a linear separator like manually. A design matrix is used in a certain statistical model, general linear models, which can contain indicator variables, so zeros and ones that indicate a group. And because it uses 1 and 0, but it says 1 where the point is. 5, 1. I'm not sure why it's called a design matrix, honestly. But this is just what you have to do for this question. So in our case, the design matrix is actually this. You want to find some linear model. You could do it with the matrix. But in our case, we're just doing it manually. So maybe that's why it has a different name here. But I think in the exam question, we will see how to work with it there. I think then it will become a lot clearer. But just remember, if you cannot fit a linear separator, we have to either define the values or we have to define a linear separator that fits. Okay. Yeah, I've never really thought about it before. Sorry, I don't know why. Okay, so let's move on to regression. So it says here, do you remember what regression was? Well, we already saw it before. We have some data points and it tries to fit the line to the data as best as possible so we can make some predictions. So here you have height and age, for example, and we have all of these data points collected. It tries to fit a line as best as possible such that if I ask, okay, if I'm 45, what is my height? Like make a prediction. So then it looks at the line. What is the value of the intersection of height of age 45? Well, you have a height of like 162, let's say. So that's what linear regression would show. So we have data points, we have a line, and the prediction looks at that line. So that's why we wanted to minimize the error value, correct? So here, actually, we're not minimizing the error value, but we're actually calculating the function itself. So the optimal linear function that fits our data. So first we were given this, and then we wanted to minimize this error value. And now we actually want to define this linear function ourselves. And how do we do this? We take these 4 steps. So the first step is to calculate the error value based on each value. So that's what we did before. Then we want to calculate the total error function based on those values. So you just sum them up. The third step is to search for this minimal function or like this optimal linear function. And you do this by calculating the derivation of the function and setting this equal to 0. And once you solve this equation, you will find a value that gives you the function that will be optimal, an optimal linear separator that fits your data. Or sorry, not a linear separator, a linear, yeah, so a linear function that fits the data. I'm sorry. So here we're not separating 2 classes. We're looking at the data points and trying to fit a line that fits the data the best. So again, let's try a recap question. So we're going to practice fitting a linear function to a number of training sets. Suppose we have 3 pairs of values for 2 features. As discussed in the lecture, according to the ML recipe, the results depend on the chosen model class. Let us calculate the optimal function according to a number of different classes. So let us start with the most simple model class to fit our training examples, which is a constant line, which we saw before. This means that we're looking for a function that looks like fx is equal to b, which is a horizontal line in the coordinate system. Then they're asking, what is the result of learning the optimal function fx from the given data? So hint, we're looking for a value of b. So let's go through this question. So the first step is to calculate the error function of each value. So remember the error function, it's here as well. And we have f of x is x. How do I fill this in this error function? I think this was the same one as before. Sorry, is b. If you know that f of x is b, how do I rewrite my error formula? Sorry. Yes, we take the sum of b minus y squared. For every value of y, we take b minus y squared, and then we sum that up. So for our 0.11, what do we get there? One, yeah. So 0. If you would fill this one in, so b minus y. Exactly, b minus 1. You get b minus 1 squared. Yes. We do the same for every single point, so we get 2, 3, and also 3, 2. So this is step 1, right? We're calculating the squared error function, so this is b minus 3, right? Because we're taking exactly 3, because we're taking y, and here it becomes 2. So that is step 1. Calculate the squared error value, and now calculate the total error value based on those values. So what do? I think I already saw it in the chat. We need to work this out such that we can sum all of these up. So this is step 2. So do you remember how to do this from high school? So it's b times b, b times minus 1. So what would be here? You have to multiply these accordingly, basically. Yes, exactly. I see b squared minus 2b plus 1. Exactly. So we're going to do that for every single one of these such that we can sum them up. So for the second one, what would I get here? B minus 3, B minus 3. Yes. Exactly. Plus 9, and then I think you guys get this one. So for the last one, we have 4b plus 4. And we sum these together. So we get 3b squared, and then yes, exactly. So minus 12b plus 14. Yes, great. So that's our step 2. Calculate the total error function based on those values. So this is what we get. Then for step 3, we want to search for the minimal function, so the optimal linear function. And we do this by calculating the derivation and setting this equal to 0 and solving it. So if we take the derivation of this error function, what is that? Does anyone know? 6b minus 12, perfect. Exactly. So that's our step A. And for our step B, we set that equal to 0. So if we solve this, what would be our B value? 2. Exactly, perfect. Because we take 12 to the other side, right? Plus 12. And then we divide it by 6. So that is indeed the case. We get B is equal to 2. Okay, last step. The value you find gives you the function that will be the optimal linear function that fits your data. Okay, so we were looking for a function that looks like fx is b, and we found our b value. So what is our optimal fitting line for this data? Yeah, so this is exactly. So if you derive something, then you write it like that. Right? Yes, so I see here people saying fx is 2. Exactly. So the derivation, that is indeed that notation, right? Do I remember correctly? Then you just do the apostrophe. Yes, exactly. So that's why I did like error apostrophe. I'm just taking the derivation of it. Okay. So indeed, fx is 2 would then be our optimal function for the data. So for this step, for these questions, you need to remember these steps. So calculate the squared error function and sum them up. Take the derivation, set it to 0, and solve it. And then based on what your function is, so again, this is very important. This could also be b plus 1, for example, then or b plus y or whatever. Then that would be our final, sorry, not b plus y. Let's say b plus 2x. Then this would be our final formula, for example. But in our case, we just have b. So then indeed fx is b is our final answer. Okay. Let's see. I think neural networks is the final one of these. And it's only 3 slides. Do you want me to go through it now and then we have a break? And then we can do the exam questions. Okay, great. So a neural network. So a neural network, neural networks are a set of algorithms modeled loosely after the human brain, basically. And they are designed to recognize certain patterns. So they interpret sensory data through a kind of machine perception, labeling, clustering, or raw input. So basically what it comes down to is neural networks help us cluster and classify, but you don't really need to know the theory behind how they work exactly. But here you have something called an input layer, a hidden layer, and the output layer. So for us here, for the exam, you want to know what is my value for the output. So some other things that you have to know is, okay, how do I calculate this? You use this formula here, which is basically just the sum of the values of its children times their edge weights, as you can see here. You multiply it by their edge weights. And one important thing is that if you see a black node, this is called the bias node, and its value is just always 1. So that's something you really need to remember. Okay. So then again, the formula you need to use is just you take the value of the children times the weight. Is that the only function it has? Yes, this is just all you need to know. Oh, the bias node. Yeah, it just only, the value is 1. Yeah, exactly. Yes, okay. So let's do a little recap for this one, since this is all you need to know. So we see a basic multi-layer feedward forward neural network with the weights and the values on the input nodes, and it has no activation function, so it's just a linear function. The black node is called the bias node. And what is the value of the output node marked x? Okay, so what is our first step here? Does anyone know? What do we want to calculate first before finding x? A and B, exactly, because we need these values for A and B in order to calculate x. So, okay, let's take A. So what was the formula again? We take the value of its children and we multiply that by their edge weights. So for A, what do I need to sum up here? Exactly, we do 1 times 1 and 2 times 0. So that is 1. So here we can update the value kind of. So this is then 1. Okay, as you said, we have to do the same for B. So what happens for B? 2 times 1, 3 times 1, perfect. Because the bias node is 1, remember. So that is indeed this value here, and that is 5. Oh yeah, 1 times 3, I guess. Yeah. Okay, so now we know the values of A and B. So how do we calculate our x value? 1 times 6 plus 5 times 2. Perfect. Yes, you take the values of a and b. So that gives us 16. So then the question is, what is the value marked on the output node? That is 16 in this case. Okay. So neural networks, usually these questions are pretty doable. Students don't really make a lot of mistakes with them. So just remember the formula and remember that the bias node is 1. That's all you need to know. You multiply the children by their weights, and that's it. Okay. So now we're going into our exam questions. So let's have our 15-minute break. So until, or maybe, is the formula not given? I don't think it is on the cheat sheet. I'm not sure. Yeah, I think 12:10, or we can do 12:15, so we can have like a little lunch break, and then the rest of the 45 minutes we can do exam questions. What do you guys prefer? 12:10? Okay. Then I'll grab something to eat. I hope I'll be back in time. And then we'll start with the exam questions at 12:10. Okay, so you can ask some questions in the chat, but I'll be right back. Okay. So I see a question stating, what is a text feature vector? So if we go back to what we just did in k-nearest neighbors, so you can convert sentences into feature vectors. First, you pre-process them by getting this. And then to write these vectors down, you put it in the table like that. But in a sense, the actual vectors then would be 1, 1, 0, 0 in this case. So it's basically just your row from the table. In this case, they asked you to write it down in a table, but in a sense, the feature vector could be either in the table or as a vector. Yeah, it has to do with like the text classification. So first you pre-process it and then you write down the feature vectors, which are just the zeros and ones. All right. Let's see. So now we're at the exam questions. I think I prepared quite a few, if I remember correctly. And let's just go through them together. I think I added a few. Okay. So now we have the final preparation in which we will go through some exam questions. So I think the best way to go through these is for you to do them yourself. Then what you can do is you can message your answer to me in the chat, like privately, so people don't see your answer. And then I can see how many people are done. And then afterwards we will discuss it together. And then I'll probably ask one of you to explain how you did it, and we'll go through it. Okay, does that sound good? So I'll give you guys some time just to solve it. And then if you send your message only to me in the Zoom chat, I can see how far you guys are, how many of you are done, and then we can discuss the answer when a lot of you has answered the question. So I give everyone some time to solve it. So this first one is about probability, and they want you, given this full joint probability distribution as above, you want to calculate the probability of cavity given toothache and catch. So I'll just give you guys some time. And send your answers to me in the Zoom chat privately, so then I can see when you guys are ready. I think this is the best, so you all get a bit of preparation time. Sorry, I should probably specify that this is an OR.
Is it
So,
if it's
yeah,
a comma, it's a and, right?
yeah, sorry, I did say and. I think for this one I meant to say or. I'm sorry. I think the notation was wrong. So you will either be given toothache and catch or toothache or catch. Sorry. Yeah. Sorry, guys. I think I added the notation in incorrectly, but it is indeed or. So when you're done, just send me your answer. If you don't know, you can just send me don't know, so I know I'm not waiting on you to solve it. Okay. Okay. All right. So let's see. Maybe Ruvantika, could you explain me how you got to your answer?
The 0.461, right?
Yeah.
Yeah. I did that one by first calculating the value for when you do have a cavity.
Mhm.
So the probability of you having a cavity given that you have a toothache or catch.
Mm-hmm.
And that was then then you have to use the formula. I don't remember what formula it is.
Oh yeah, the
But-
conditional probability one, right?
Yeah, that one. Exactly.
Yes. So that is indeed correct.
Isn't it B? Or no, my bad.
Oh yeah. So then how did you fill this one in?
I'm not sure if I did this right actually looking at the formula, but I'll just say how I did it anyways. I did 108 plus 0.
Wait, am I?
Because I used the PA comma B divided by PB.
Am I writing down the formula incorrectly? No.
Yeah, I think that's a different formula.
No, I think you guys are talking. This is this is base rule. I'm sorry. Yeah, you're right. They look very similar. Sorry. Yes. Yes, I'm sorry. So it is indeed B, yeah, A and B, and then divided by B, right? Yes. So I think you did that correctly.
Yeah. So yeah, that's the formula I used, and I then did 0.108 plus 0.012 plus 0.072.
Sorry, 0.108 plus.
0.012.
Oh yeah.
Yeah.
And then?
Oh, I didn't add the 0.0808 at the end.
Oh yeah, you're right. Sorry. This is for cavity and toothache or catch. So you take cavity
Yes.
and you take toothache and you take catch. So then. Oh yeah,
'Cause there's-
toothache or catch, of course. Yes, so you take these and you take these. Yes.
Yeah. And then I divided that by the probability of toothache or catch, which was 0.108 plus 0.016 plus 0.012
Mhm.
0.06 plus 0.072 plus 0.144. And
Yes.
all of that together was a 0.416.
Yes, exactly.
Yeah.
And then
And the final value for this one was 0.4615.
yes, perfect. So that is the first value of our vector, and then for the second one?
The second one was then, for the probability of no cavity given that you have a toothache or catch,
Mm-hmm.
which I did 0.016 plus 0.064 plus 0.144,
Mm-hmm.
and then divide that by 0.416 again,
Perfect.
and that is 0.5385.
Okay, exactly. So then the vector
is 0.4615, comma 0.5385. And then the closing bracket thing.
yes, exactly. So let's see, I think other people had a similar answer. Yes. Okay, so why are we not including no toothache and no catch in the first one? Because it has to be a toothache or a catch. Yeah, so I think people are answering that for you. So someone also said, okay, I see where I went wrong. Is this very, I see a lot of people said don't know. How did we get, oh yeah, that is basically just toothache or catch. So you take everything of the toothache and everything where catch is true. So these values. Yes. Why didn't you just do 1 minus for the second value? You could do that, yeah, but I feel like this is important to know like what you're actually doing. And maybe with the rounding, it gets a bit different. Yes, exactly. No toothache, no catch. Oh yeah, for the last one, it would be no toothache, no catch. So we leave that one out, and the rest we do take. Okay, so that was great. Thanks, Rufantika. You had the correct answer indeed. So let's see if we were correct. Yes, exactly. So I think there was a rounding mistake here, but it is indeed 5. Like that. So for everyone that had a different answer or wasn't sure how to approach this, do you get the answer? Do you have any questions about how we got here or any questions about the theory behind it, or does it make sense now? Yeah, I think I made a mistake here with the notation. Sorry, I feel like usually it means and indeed, but I meant or. Yes, sorry. Okay. I think for the rest it was also okay. So that's good. I think probability is quite a big part of this exam. So there are a lot of types of probability questions. So let's just go through another one for the joint probability distribution. This one is a bit different. This one says, consider the following full joint probability distribution, and then it asks you which statements are true. So there could be multiple correct answers, and I'll give you guys, again, some time to answer this one. So my advice is just to go over the statements, check like one by one which one is correct, which one is incorrect, stuff like that. So just send me the letters from which statements you think are true.
Mara, the screen disappeared, so we can't see the question anymore.
Yeah, sorry. Wait.
Yes.
Yeah.
Thank you.
Is it working for you guys? Oh god. No. Is it? Oh, fuck. Okay. Yeah. Sorry. Sorry, it was black. Okay. I'm sorry, guys. Let's see. I got a few answers coming in. 1, 2, 3, 4, 5. Let's wait a bit longer. Again, if you don't know, just maybe try to guess or say don't know. Okay. Let's see. Maybe Kevin, could you tell me how you got to your answers?
Yeah, sure. I thought A wasn't true because the total probability is 1 and P true, Q true, and R true is only true in one case, which is 0.26, so that one's false.
Yeah, for this one it does sorry, it does
says
say
or.
it says or, but you are correct indeed. Like this one wouldn't be there because it's all false, so it does not sum up to 1.
Yeah, well, lucky then.
Yeah, but I think your reasoning was kind of in the same direction. So indeed,
Yeah.
A is not true.
Yeah, and then for B, I added all of the probabilities of the cases where R is false. So that's 0.33, 0.14, 0.08, and 0.01.
Mhm.
And that's correct. So B is true.
Yes. So B.
Then for C, I wasn't quite sure.
Mhm.
So I chose not to say that it was true.
Okay, for this one, what it says here is if we remember the conditional probability formula, so this one, and you would actually calculate the values, you would see that they're not true, but also there's this little knot here. So Q being true, given R being false, is not the same as R being true given Q being true, is usually the case as well with conditional probability. Even if they're both true, that doesn't necessarily mean that they're equal. In most cases, they're not. But here also R is false here, so that also makes it not correct at all. So that's why that one is indeed false. Yeah, like that. Or wait. So in both cases, these are probably not the same. So this is indeed false. And then for D?
For D, we would add all of the values where all of the probability values where Q is true, and that's 0.26, 0.33, 0.03, and 0.08, and that's not equal to 0.26, so that's false.
Exactly.
Then for E, of the cases where both P and Q are true, the sum of those, and that's only the top 2 rows.
Exactly.
So that's indeed 0.59, which is correct. And then for F, you would do the same thing, but all cases where R is false. And we already knew that B was true because it amounted to 0.56. So we can just say that F is false.
Okay, perfect. Great. Thank you. So I see some people saying C is not correct. So yeah, that's the main mistake I think I saw. So for C, is the answer always the case, or are there any values that can make that statement true? I think if they would both be 0, then they are equal. But in any other case, I feel like they're like, because you have to use this formula, right? There are not really a lot of cases where you would yield the same, or if they are the same value, maybe like 1 divided by 1. But then you would still have to add them up here. Yeah, okay, so this is the given, right? So in our case here, okay, let's try. So Q is true given R is false. That's the first one. Yeah, exactly. So you would apply the same formula. So you would do every value where Q is true and R is false. So Q is true, R is false is this one and that one, I believe. So then we do 0.33 plus 0.08, and you divide that by P of B. So that is R is false. So we know that that is 0.56. So let's do that. .73. And then indeed we can try the same thing. For R is true, given Q is true. Also the fact that here it's R is false and there it is R is true. So that already makes it not really the same. Let's see. R is true and Q is true. This one, that one. So we have 0.26 plus 0.03 divided by Q is true. So that is these added together. So I got 0.7 here. So then we do 0.26 plus 0.03 divided by 0.7 is 0.41. Yeah. You could also divide it by R is true. No, you couldn't, because the formula is A given B is A and B divided by B. That's the formula. So you have to divide it by B, which is Q is true. Like that. Does that make sense to everyone? How I got to the values? Oh, okay. That's okay. Yeah, this is probability. This is not logic. So, yeah. So as you can see, these are not equal. So that is why C is false. So if you're uncertain, you can just calculate the answers and then you get to this. So let's see if we're correct. Yes, B and E. So I think I just highlighted this is like P, this is E, for example. P is Q and Q is true. Wait, did I? Oh yeah, sorry, I was looking at R. Yes, B is Q and Q is true. So that is for E, the answer here. So I hope that makes sense. I would just, like Kevin said, you just go through each statement, see, okay, is it true, is it not true, and why? And that is how you get there. Okay, let's move on. So another probability question. This one shouldn't take as long. It says, which one is not symmetric? I think we just touched on that. So let's see what you guys think. Okay, I'm seeing all of you choosing the same one, so that's good. Okay. I'll give you guys a bit more time. Yeah, this was an exam question. So, but we also just saw it. So with the theory you know about probability, I feel like you should be able to know why this is the case. Okay, so Artemis, could you tell me why you chose that answer?
It was kind of a guess because I'm not sure what
Okay.
not symmetric means, but C is the only one that stand out because A or B or B or A, isn't it the same thing?
This is the given sign. And not symmetric means what it says here. So not symmetric means that if A union B is one value, then this value should always be the same. So if it's not symmetric, then it's not always equal to each other.
Oh, so C is because they're usually not the same, like we saw in the question before, but the others
Exactly.
are usually the same. Yeah.
Exactly, because with A union B and B union A, like if you would take the conditional probability here, sorry, not conditional, but the union. So if P true and Q true, that is the same as if we would say Q is true and P is true, right? We would get the same answer. Same with OR. We would also get the same answer, but indeed with conditional probability. Oh, sorry. Did you have a question?
No, it's fine.
Oh, okay. With this one, indeed, you could have, as we just saw here, that these are not the same. So indeed, for conditional probability, that's something to remember. It is not symmetric because OR means you get the same outcome with the union. So and you also get the same outcome because that doesn't change it. But with the conditional probability, because you're making use of this formula here, it means that it's not always symmetric. So not always is A given B the same as P given A. So it's basically which expression is not false.
Why is it saying then that it's like P, A, or B is not always equals? So is that just like a false statement? Is that what, like there's two false statements and one true? Is that the point of the question? Or is it, because it's just two of these statements are not true, right?
No, it's, I mean, it asks like which one is not symmetric. So I guess just which one is true.
Yeah, okay.
Yeah, so this one is true. These are indeed false. Yeah. So the question is basically which expression is not false. Exactly. So let's check. Yes, it is indeed conditional probability because that is not symmetric. It just asks which expression is not symmetric. In this case, it's C because these two are both symmetric. Okay. So we still have 15 minutes left. Let's see. So this one was asked in the chat, but I thought I might not answer it because we're doing it now. So this uses Bayes' rule, and it's about the chance of rain during the day given that the morning is cloudy. So let's see if you guys can figure this out using Bayes' rule. That's very important. Okay, so I'm seeing the answers coming in. Let's wait a bit more. Okay, so let's see. Bob, how did you tackle this question? How did you solve it?
So I recognized based on the question that we should use the Bayes theorem. So I wrote that formula down.
Mm-hmm. So what is that
Um,
again?
Yeah, I did probability that R given C equals probability C given R times probability of R. Divide that all by probability of C.
Mm-hmm.
And then I just, yeah, with the given information, I just plugged it in.
Okay, so which values did you have for these?
0.5 times 0.1 divided by 0.125. No, sorry, 0.4.
Yes, exactly. And that is indeed 0.125. So yes, this is indeed how you would do it. I saw a lot of people also got the answer. I think one person mixed up the formula maybe. But indeed, so we're using Bayes' rule. So that is the one I wrote down before. So A given B is B given A times B divided by this one. Is this formula on the cheat sheet? Let me double check. Does someone know? I feel like it should. I don't think so. Okay, let me check. Okay, I don't see Bayes' rule on the cheat sheet. So indeed, you would have to memorize this one. Yeah, I'm sorry, I don't see it. Now that you say it, I feel like it should be. Okay. I will maybe let Stefan know again. Maybe I could add it still. Okay, I'm a little confused with the wording. Okay, let's look at it together. So 50% of all rainy days start off cloudy. So what is our given information here? What is the fact that we know for sure? Is it a rainy day or is it a cloudy day? It's given a rainy day. Okay, so almost. So it says 50% of all rainy days start off cloudy. So it's the probability that we get cloudy given that it is a rainy day. So that is 0.5. And for the second one, it says cloudy mornings are common as about 50% starts off cloudy. Okay, so that is cloudy. Sorry, 40%. So 40. And lastly, this month is usually a dry month. Only 10% are rainy days. So the probability that it is a rainy day is 10%. Okay? And then what is the chance of rain during the day? Given that the morning is cloudy. So this is our given information. And what is the probability of the chance of rain given that it is cloudy? With here, it says, I guess start off cloudy might be the confusing parts here, right? So it says of all rainy days. So that is the fact we've been given. It is a rainy day. What is the probability that it is cloudy? So that's why it's C given R. Yes, and then we want to indeed have what is the chance of rain given that it is cloudy. And then you make the formula and you fill in the values. So PC given R is the chance of the day being cloudy given that it is a rainy day. Yes, exactly. Yeah, the dry month, I mean, it says between the brackets 10% tend to be rainy. So I feel like from that you can see, okay, 10% is rain. Okay, great. So let's see how much time we have left. Let's see, did we do it correctly? Yes, so rain given cloudy is cloudy given rain times rain divided by cloudy. And that is indeed 0.125. So is that clear for everyone? I think few of you did get it correct, so that's good. Most of you. Yes, okay, great. So let's do a precision and recall question next. So the formulas are on the cheat sheet, but you have to fill them in correctly. So that is the case here. I didn't know Bayes' rule wasn't on the cheat sheet. Let me check it out. I'll check the one from last year. Oh. Oh wait, I think I know maybe. So on the cheat sheet you have for conditional probability, so it's not there directly, but it says oh no, wait, that's another one. Or is it? Yeah, it is another one, never mind. Right. Yeah, no, so Bayes' rule is not on the formula sheet, so you have to memorize that one. Okay, I'm seeing a lot of good answers. So, Jacqueline, how did you get to your answer?
For precision, I use the formula true positive divided by true positive plus false positive.
Mm-hmm.
And in this case, true positive would be 240.
Mm-hmm.
And the false positive would be 60. So you do 240 divided by 240 plus 60,
Mm-hmm.
which is 0.8.
Yes.
And for the recall, it's the same formula, but instead of false positive, you have false negative,
Mm-hmm.
which is 80. So you do 240 divided by 240 plus 80,
Mm-hmm.
which is 0.75.
Yes, perfect. Exactly. So I think most of you got this one correct. Let's check. Yes, so 0.8 and it's 0.75. Okay. So yeah, just a quick announcement, I guess. Bayes' rule is not on the cheat sheet, so you will have to memorize that one. Just so everyone knows. So this one. Yeah, I just remembered that during the last meeting, we decided not to add this one in. Let's see, why is false negative 80? So this is the false negative value. So it's predicted to be false. Sorry, it's predicted negative, but it was actually positive. So it was a false assumption. So this is false negative. Yeah.
Lady.
Yes, great. Yeah, no, sorry. I remember we asked him during last meeting, but we decided to keep it out because we still wanted you guys to memorize something, or I think I was sick during that meeting. I don't really remember what was being said. But so Bayes' rule, you have to memorize that one. I think the easiest way to memorize it is that since A is like on the last part here, that is what you have to multiply it with. That's how I remember it. And then divide by B. Okay, so I think most of you got that one. So we're already at 1 o'clock. Yes, RDFS rule 10 is on the cheat sheet, so that is good. So it's only the Bayesian rule then, I think. Bayes rule, sorry. So I feel like that's not too bad. So I have a lot of other exam questions, but I see it's one already. So before you go, I would like to ask you, yes, it's an updated cheat sheet version. I think he uploaded it to like the test vision thing, but I don't think he uploaded it on Canvas. So yeah, before you go, I would like to ask you to scan this QR code and fill in the evaluation form, which really helps Athena Studies as well as me. And then I have a lot of other exam questions on the rest of the slides. And of course, you can use the 2 practice exams from 2020 and 2021. I think those are quite representative of what will be in the exam. Of course, not anything about sets or fuzzy logic. We did not cover those, but the rest is in there. And then for RDFS rules and like the modus ponens, the rule-based reasoning, that is all in the slides. So I would advise you to go through those. And I will send the entirety of the slides to you so you can check out the other exam questions as well. But I see it's already 1. So yeah, once again, please scan this QR code and fill in the evaluation form. And then I'm afraid that's all the time we have for today. Is there a summary of all concepts of the ethics part? I put down some of them on the slide, but I don't think it covers all of them. So yeah. It's like the ethics and the philosophy of mind, the 2 lectures. I think we sent them in the group chat. There is a YouTube link to old lectures. Is only ethics and open questions, or is only ethics an open question, or are there any other open questions? From my knowledge, it is an open question, like only the ethics part, I believe. Like the other open questions could be like a Bayesian network question where you just have, no, we don't have fuzzy logic, no. The only open questions we have are like fill in the value, like this one. It's kind of an open question, but it's like you don't have to write anything, you just have to fill in the value. So I wouldn't really call that an open question. I feel like ethics and philosophy of mind were the only open questions. No, so no fuzzy logic, no sets, but the rest, or just everything from the Athena slides, of course. That's what you have to know. So you can check out one of the first slides is the exam, what is it called? Evaluation or something? Exam analysis. And there I put down all the theory that you need to know. Like all the points you need to know. Are there ethics multiple choice questions? I think it will be an open question. I think there were 1 or 2 open questions, if I remember correctly. But yeah, I'll stick around for 2 more minutes or something, so you can scan this code, ask me any questions, and otherwise you're free to go. So thank you very much for your participation. I hope it was helpful. And then, of course, if you have any questions, ask them in the group chat. If you scroll up, I worked out all the Bayesian network questions for you as well. And yeah, I mean, good luck with your exam already. Yeah, so I have a lot more questions here prepared, actually. So for ethics open questions, I discussed this yesterday. And then, yeah, of course, good luck. Good luck with your exam. And then, yeah, that's it. I won't see you all again as a TA, sadly. So thank you very much. Happy holidays. Yes, happy holidays, everyone. Bye-bye. Happy holidays.
Thank you. Bye-bye.
Yes, thank you.
Thank you. Bye.